So I'm looking at right now our questions. I don't see any questions on the doc right here, but I'll kind of just go through a little bit what we're going to do today. We last time talked about convolutional neural nets. We didn't go into full detail. Maybe we'll do that in the future. I think maybe even today if we have time, but we'll see. We today are going to finish up section 39, natural language processing. We'll go through that because I think even if you don't expect to be doing a lot of natural language processing in your future job, I think it's an important aspect of data science that's like useful to be familiar with, because I like to tell people it's like language has so much information. It's like information dense, and understanding how to extract that information to do something useful can give some really great results. So if you don't learn any NLP, it's kind of like basically saying you're not going to look at anything that has, decimal points. It's kind of like it's restrictive in that way. So I think it's useful to say, hey, what's some at least basic NLP stuff we're doing? Are we going to build, something that's going to generate text and stuff like GPT-2, GPT-3 that recently came out? No, maybe that could be fun stuff, but it might not necessarily be useful for your specific use case. But understanding how to say, hey, if we're getting customer reviews and stuff like this, with a business, how do we process information? Maybe you have like hundreds of thousands of reviews sometimes, or, comments or something like that. It might be useful to say, hey, what's the overall understanding of what's going on with this textual information? And we can actually do some pretty interesting stuff, even with the basics. So we'll talk about that today. But before I get into it, does anyone have any questions that they want to start off on the bat? That's been lingering in their head or anything like that? Pretty good? Cool. So we'll get right into it. And of course, as always, you guys can always interrupt me if you guys see something like, hey, like I do have a question on this, or, oh, like, can you talk more about this area? So again, I like to show you guys where it comes from. That way you guys can always find it later. This is just the repo, right? You guys all know how to find that, NLP. And then we're just going to talk about more or less all of this stuff. We're probably going to leave sequence to sequence models. We'll see if we have enough time, but that's going to be the last thing we do, if anything. Okay, so let's go intro to NLP. Before I kind of go there, just give me a thumbs up. Who has gone through or at least started section 39, the natural language processing? Okay, cool. I think I see most people who have the videos up giving me a thumbs up. So that's good. If you haven't, no worries. We're going to kind of go through a lot of this stuff. If you've gone through the section, it's going to be review. I'm just kind of giving you guys a perspective on it. But if you haven't gone through it, you should be able to follow along fine. So one thing, kind of natural language processing, NLP, basically the idea is that we have natural language, which is different from like a structured language. You can think of like structured language being like logic, mathematics, programming in Python. They're basically very strict rules in that if those rules break, like if you break those rules, you have just invalid like usage. Like if you break the rules of how logic works, if you break the rules of how the mathematics work, you are no longer speaking of anything like meaningful. Versus natural language, it's a little more fluid, complex, and unstructured. So they're like, and people say like, well, unstructured, we have grammar. It's like, well, we have grammar, but you can kind of like, you can break the rules of grammar. And this is where I say the rules of grammar, there's no official rules of grammar, but like you can break the rules of grammar and people still can more or less understand you. Think of like, if you're learning like another language, a second language, you might speak for like broken English or something like that. You could more or less still understand what the person is saying. And that's the point of natural language. Or we add new things into the language that didn't exist previously. I think of the words like, like what the heck, or like, oh, that's hella cool. Like that's like those words by themselves might not be originally like if I say cool, it's like, oh, we kind of understand like cool could be like cold and stuff, but it could also be like, oh, that is like really awesome. Like, it's a different kind of connotation. And also like hecka cool or hella cool or something like that. Sorry, I'm from Bay Area, so that's what I hear a lot of. But like that stuff is like, oh, what is that emphasis? There's a lot of interesting things with language. If you're interested in linguistics, it's a really cool area. I'm not a linguist. I always think like in another life, maybe I wouldn't go in that direction, but know that there's a whole bunch of cool stuff you can like look into like natural language. But that's kind of the difference between the two. And computers are kind of bridging this gap between processing words and phrases, like identifying speech, keywords and stuff like this, parsing sentences, statements, questions, right? All that good stuff. And then more advanced techniques like tone and sentiment analysis. So actually saying, when someone talks, like there is like a certain like there's meaning behind just the words themselves. Think of the reason why like writing an email versus speaking to someone is a very different action. I would even say having a text message is a very different action than writing an email. It definitely has different connotations and different styles that is about communication. Sentiment analysis, you'll see this a lot, sentiment analysis, basically saying like, what is the meaning of this overall like sentence or corpus or whatever you're, not corpus, but like this text, like what is the intent of it? Usually sentiment analysis we talk about, was it a positive interaction, a negative interaction, neutral? Think like if a review, like an Amazon review for a product, if it's like a positive review or a negative review or a neutral review based on just the text itself. There's also document grouping and clustering, which is pretty cool. A lot of times we can do things like, if you ever hear about finding authors' works that like they write with a different pen name, is that pen name? Yeah, a different pen name and stuff like that, and try to identify that. A lot of that can be actually done with group clustering stuff, but it can also be useful to understand what kind of structure this like text has and compare it to the things that you already are familiar with. So some pretty cool stuff you can do with NLP. Some challenges of NLP. So this is where I think it's a good example of thing like why natural language processing is so difficult, even having all the tools we have. If I have this sentence right here, it's difficult for a computer to parse this correctly. It said, I was led to believe the Fire Festival would be an amazing transcendent event. I was conned. If you read most of that, like you all should pretty much understand, right? It's like, oh, that was a bad experience, right? But if you read like almost all of it, most of those sound positive, but like, except for like this con part right here, but even I took out, I was conned, I was led to believe that the Fire Festival would be an amazing transcendent event. That led to believe part right here gives you a cue like, ooh, that's not quite true. But if you look at just the words of like being like believe, Fire Festival, amazing, transcendent, you know, oh, that might be a positive thing. Where in reality, it's like, oh no, it's actually the opposite of this. So that's why this can be really difficult. You guys can probably start reading this part right here. Ambiguity, this is one of my favorite examples, is basically there's a very slight change and it means a whole bunch of different things. Or let's write this down. The pipe couldn't fit through the hole in the wall since it was too big. What is it? What is it associating?
Yeah, the pipe should be what's too big, right?
Yeah, the pipe is too big. That's what it is. And how do you know that? Because that's what pipes are, right? The pipe wouldn't fit through the hole because the pipe is just too large, right? Like that just makes sense. But if I just change one word, which is the same thing, the pipe couldn't fit through the hole in the wall since it was too small, you immediately know it is now referring to the hole, right? But the only thing that's changed is the descriptor of saying small or big. So in a lot of ways, we use our knowledge of like the world, of like how the world works to understand actually what's going on in a sentence. And imagine trying to tell a computer, like, you know, like basically, essentially, in some ways you have to, in order to properly parse natural language, you have to have at least an idea of how the world works. And I say you have to have an idea, like that's obviously very like, I'm not saying like a computer has to have like an intelligence in the sense of like a human brain, but there has to be some association with like how these things are connected, the hole in the pipe, there's a lot of connection there. This is why if you guys have looked at GPT-2, GPT-3, I think we mentioned it a few times in passing and stuff. I know Alvaro has, because he brings it up a couple times. But this is where it's really interesting to see how GPT like 3 and GPT-2 actually like try to do well in generating sentences. In some ways, it has to learn things that are not directly grammar, not directly what you would see as classical English. For example, I'll just say real quickly, GPT-3, which was trained, it's a transformer for basically natural language. And it was just given a bunch of language, like I think it's like 40 gigabytes of data, essentially, of text data, and just like basically learn from that thing. When they tested to see how well it does with like mathematics for like at least for simple 2-digit multiplication, it didn't have any real examples. I think it was like in the paper, it shows like less than 10 examples of like actual like numbers being multiplied together. But when they tested out saying, okay, let's say 72 times 47, it was like, well, it never actually saw that number or like that like instance. And you say, what's that number? There's ways you can kind of trick it to like produce these like results. It actually can be pretty accurate. And actually for 2-digit multiplication did pretty well. And what's interesting on top of that is that it made mistakes that seemed reasonable for a person to make a mistake on. And so in a lot of ways, it's kind of in its system, it's kind of learned how to do multiplication, even though multiplication really wasn't the goal of doing that. It kind of learned some extra part of like how something works so it can produce, natural language essentially, which is really interesting. And I'm pretty sure we'll hear more and more about this throughout the years as people try different things and new techniques and such. So anyway, that's why NLP can be really super challenging, but there's still a whole lot we can do. Yeah. Any questions or comments for kind of so far I've gone through? Pretty good? Cool. All right, so let's talk about like this, what we do, right? So I'm going to take this to kind of high level and talk about listening, what the NLP pipeline looks like. And then we'll actually kind of look a little bit of some code and like what this looks like and actually practicing it. So text processing involves removing the extra junk. So you can't just simply feed like you just can't feed words directly into a neural network. You could technically, because like I don't know if you guys know this, but each letter, for example, is actually represented by basically a byte, or it could be multiple bytes if it's Unicode or whatever. But basically it's a bunch of zeros and ones. Like you can essentially say each letter is a set of zeros and ones, and you could feed that into a neural network. But I'll tell you right now, it's not going to be really useful. It's going to be very large. There's a whole bunch of issues with it. And basically, could the neural network figure things out, or other machine learning algorithms figure things out? Technically, but like also it's very difficult. Because remember, when we're doing machine learning, in a lot of ways we're just encouraging the machine learning algorithm to find patterns. And if the pattern's too difficult to find, it's not going to find it. So it could technically, but it's unlikely. So the first step we really have to do is processing text. And really what that means is basically getting a representation of the language being used. And so a lot of ways, like I mentioned here, is like that extra junk, is that we're essentially extracting like the important parts of a sentence, of natural language and such. We're trying to pull those features out and be able to feed those features into our machine learning algorithm to do better prediction, get a better analysis of what's going on. And basically when I say like making those features, that's going to be a mathematical representation of some sort. Think like vectors and matrices and tensors. Okay. So first things like features extraction. How do we do this? So there's a few ways we can kind of represent this. I'll kind of talk about a couple that are here. There's actual graph representation. So, you know what? This is not going to work really well. No, it does work. So there's something called WordNet, for example. So I just kind of put a link here. One, we can actually have a graphical representation of like how things are connected together and stuff like this. If you're curious, you can look into WordNet, which is pretty cool of seeing like how these words and like phrases are connected together. It's a whole different thing. This can take a lot of work. And also like, then you have to consider, well, what if there's a new word that was not considered in this word net and stuff like this? Or you have a bunch of texts that have different spellings and stuff like that, but mean something different. Like, so this can be kind of difficult to make sure you encompass everything you need. So we're not going to talk too much about this one, but it's a really interesting one. Document level. Document level, like if you read the curriculum, talk about bag of words, doc to vec. Basically the idea here is that we are looking at like a set of texts and seeing essentially like what's in it, like an overall, how do I say this? Like you're looking at like maybe a sentence or maybe even multiple sentences and getting a feel for what is the overall like meaning behind this. So this is really useful for sentiment analysis, spam detection. A spam email tends to look different than a typical email that you would want to have go through. So we don't need to know the specific details of every single word in there. We really just need the overall document, like what this looks like. Same thing with sentiment analysis, where like, is it positive or negative? We don't need to know every single word. We just need to know the overall feel of that text. Okay, make sense so far? Cool. All right. The other parts we can go into even further in the words and phrases. And so this is where we get to word to vec and glove. This is really useful for text generation and machine translation. So imagine when you actually do translation, you need to know every single word. Like every single word is an important aspect of the translation itself. And of course, there's issues with this too, just and even the sense of like having in traditional English that we've been using, there isn't a lot of genderless pronouns, for example. Like a lot of things are gendered, like in the sense like there is no generic he or she, like where the gender is unknown. Now, this is where I think it's really fascinating. It's like one thing that we kind of tended to agree on socially, and it seems to be been doing this direction. It seems to be really pushed forward, is using the word they for like non-gender specific, person, But what's kind of cool about that is like they is actually plural. And this is where I love to argue with English teachers, because I know a few that say like, they is they is plural. I'm like, English is what you make it. Like that's like if everyone accepts what you understand, like that's the new norm. So they is exactly going through that. I'd be interested to see how much text will have changed and observed in like the next like 15, 20 years. I like no one's even going to bat an eye at they in the few years from now. And not just because, I mean, there's a whole bunch of reasons we could go into, but I think also like people been using this like as a kid. I remember everyone uses the word they, like as like I was like, oh, it's them, like even though they're talking about one person. So anyway, language evolves. I think someone unmuted. I saw. Any questions, comments? Okay, cool. So anyway, that's kind of like some going through. Oh, and I said like machine translation, right? Okay, so after we do our feature extraction, saying like what level do we need to extract information from, we can actually go talk about modeling. And so modeling allows us basically, what's nice is that if we have a mathematical representation and numerical representation, we can actually use a lot of the machine learning algorithms we already know and love. Like we don't have to redesign something completely from scratch. Now, sometimes you'll see something really interesting in a research paper, but in general, the idea is that we will, in our pipeline, is to basically extract something and to create a numerical representation of our text that we care about, and then modeling from there. So it's pretty cool. So that's why this is, I say, is super important to understand like what we can do with NLP, because then you can just use your normal data science skills to basically at least do some analysis and prediction. Okay. So I have a little example of a pipeline. I can't remember off the, like, I feel like I usually try to reference where I find these things, and I cannot remember that this came from a project I had done or something, maybe a little gist from GitHub. But this is kind of a good example of like what this might look like in a pipeline. And so here, for example, like this is like the whole code itself, and this code wouldn't run. Like you can see the functions won't, I mean, maybe it does run, but I don't think it will run completely. You'll probably come across an error at least once. But you can see here basically your libraries and your what's it called, like your imports and stuff. And you can see pandas, we have regex right here. NLTK is a very common natural language processing tool. It's also called natural language, oh my gosh, toolkit, there it is, NLTK. And so you can actually have a couple things that are going to be specific to natural language, but then you can see a lot of these things right here. This is all sklearn. Like most of this, except for like this last part right here, is stuff you've already probably seen, and this is exactly just like what's it called, like using machine learning like you normally with sklearn, scikit-learn. And then you can see feature extraction right here. This is much more specific to natural language, count vectorizer, TF-IDF transformer. You can see this regex, for example, which can be really helpful. I will say for the record, regex, regular expressions, is not an easy thing if you don't know it. I say every year to myself, I make almost like a New Year's resolution, be like, I'm gonna learn regex better than I have it. I still have to look things up all the time for regex. So don't feel like you should be able to look at this and understand immediately what's going on. But just know basically you're looking for patterns for how the language is structured. It's like a URL. You can see the first part is our load data. So this doesn't look too crazy or anything like that. Then our tokenize, which we'll talk about what tokenize is. Basically, this is taking the word, the text itself and creating essentially the elements that we're going to use to actually feed into our, what's it called, into our pipeline. So you can see here basically is like that we're kind of taking, you can kind of read this a little bit, you're just looking for each URL, you're taking the text, it looks like these tokens, we have these tokens right here, we're doing some cleaning, we're doing clean tokens, and just think tokens as being like, oh, there's separate little elements that represent something in the text itself. And then you can see display results, this is nothing too special. And then the actual main, so you can actually see the full pipeline, this is what it'll do. Essentially like, hey, we hit load the data, which you can see was kind of coming up from here. We should tokenize at some point, here we go. Count vectorizer, so we'll talk about what these look like. Tokenize, we actually have a TF-IDF, so basically we're doing some feature extraction between these two, and then we actually use our classifier right here, random forest. Hopefully, I know I wasn't with you guys when you guys went over pipeline, but pipeline is something from sklearn, which is super useful. You can basically string apart essentially all the way from like cleaning your data all the way to actually modeling your data. So this is a really useful thing that maybe we'll talk about in office hours one day again. But anyway, you have the pipeline, you fit your training data, you make your predictions, and then you see, hey, how well did I do? And that's the whole thing. So you can see like really most of this, like if you looked at this guy and didn't really understand this, but you kind of got the idea, it's basically just another machine learning algorithm. And this is where the real meat happens of natural language. And most of that is actually going to be within this tokenizer right here, which is just defined by this guy. And you can actually use a tokenizer that's already defined in here. You can have to do this one, but you can make your own tokenizers and such. So it's actually not too bad of a process. Anyway, that's like a really quick overview of what this will look like. We'll now go into details of like how to actually do this processing. But any questions like or comments that came across?
Not a question about this,
Yeah.
but I just want to remind you of something that you mentioned. You said you were going to go over at some point baselining,
Oh, baselining, like the baseline model?
creating baselines, how you go about actually figuring out a baseline for your model.
Yeah, we can definitely talk about that. Tell you what, because next week is kind of like much more office hours for the Mod 4 project. So that can definitely be something we talk about next time. Yeah, that's a good one because that's not just NLP or any specific model. I think it's an important part to understand like how do you make a baseline and like what does that even mean? And I think it's something that's easily ignored. But yeah, good. Tell you what, Alvaro, actually message me right now and that way I'll remember it and then I'll make sure to make that for next time. Okay, cool. All right, other than that, I'll just move on then to our next part. So I think what we're going to talk about next is text processing itself. So we talked about like, okay, now we have a text. We're going to really do, what's this first part right here? Like actually getting to the point where we can actually do anything with natural language. So text processing. So first of all, it's important to always understand like where the text originated from. So you can think of things like, is it speech? Is it a web page? Is it a Word doc? Other text formats? Like it's going to have different formatting depending how you pull it up. So for example, web pages like web scraping, you're going to have HTML tags and stuff like that. You'd want to make sure you clean that out because that's not going to be necessarily important for your natural language processing. And the reason why we might want to remove that, even if it gives extra information, it makes it easier to generalize our pipeline then, right? If we can get it to the point where anything you feed into and we process it into this format, then now all of a sudden we can do whatever. We can use speech, we can use text, if someone types in, we can pull from a website. So that's really why it's important to like really think about like where this text came from in the sense of like what it looks like to pre-process it. So anyway, for the most part though, we'll try to convert it into like text, like words, and we might remove some stuff, but we'll talk about what that looks like in a bit. Okay, removing irrelevant information. So this one, for example, I have a little sentence I made up. The dogs in Alaska are cold, hungry, and lonely. There's some redundant information. And I don't know about you guys, like English is technically my first language, but I always feel like I want to like just like chunk up my English a lot. I don't know if that's just because of like where like how I grew up or something like that, but like I always feel like these are redundant stuff like in and stuff like this. It doesn't really give real information. So there's a lot of stuff that's kind of redundant and not necessary for written language. So for example, punctuation can likely be just removed. Maybe you get some information from being a question mark, exclamation point, or period. For the most part, it's just like, oh, that's the end of the sentence. So in a lot of ways, punctuation means nothing. Capitalization, like think of like, it doesn't really give much information. Like I like to tell people like, it doesn't give much information because like when we speak, we don't have capitalization while we're speaking, right? That kind of makes sense. And so in a lot of ways is that you don't necessarily need capitalization to actually give real information. A lot of the stuff is, again, natural language is so informational dense, like we can remove stuff. There are arguments, like I will tell you, English will say like, there are information like why we capitalize things. Partly is for importance, which is interesting. Sorry, I'm gonna go on a sidetrack here, but like, you can see this from sometimes in certain authors. For example, the author who wrote the Adventures of Winnie the Pooh, like the original Winnie the Pooh, he loves to use capitalization and not words that you would typically capitalize, and basically just to give emphasis for that word. So anyway, capitalization generally in NLP, we usually get rid of that stuff. And then also common words that don't really mean much, like a, the, are, of. And this is where, again, like I would argue, or maybe someone would argue saying there is information there, but I'll argue saying it doesn't give much information. And because natural language is so informational dense, we're trying to get rid of that density so we can get to the point where we get the real meat of the context. So that's why we get rid of, in like English, for example, a, the, are, of. And note that different languages will have different words that you would consider redundant or unnecessary. Okay, makes sense so far? Any questions, comments? Yeah. Basically, this whole thing is going to be about like how your English teacher is like, you don't need to listen to them anymore. So anyway, all right. So useful tools, interesting NLTK, so Natural Language Toolkit. So NLTK is open to open source and everything like that. They have some great documentation on there. However, note that NLTK tends to be a little more, I think sometimes you get spoiled with sklearn sometimes because it's so, like, I think sklearn is actually well documented. NLTKs tend to be more geared towards, I don't know, a different set of people, if that makes sense. But you can usually figure out a lot of what's going on there. It's, I don't know how to explain this in an easy, direct way, but like scikit-learn uses a lot of like classes and objects and stuff like this, like object-oriented programming. NLTK just loves their like lists and dictionaries built within itself, and it's just, it can feel a little clunky sometimes. But I don't know, maybe you guys have a different experience. But note there's also a book on NLTK. For the record, you can actually buy this book like in print, but I would never recommend actually buying the NLTK book, just because like this is actually updated. This is actually the version of the updated book. And I think it even says like, yeah, there are no current plans for a second edition of the book. So like basically they keep fixing these stuff, and you can basically just reference the whole book within here. And it's literally the same thing as what you would like buy in print. The only reason I guess you could find it like if you happen to cross it, but there's gonna be some errors and stuff, because I've come across errors in my life of like going through the documentation of NLTK and I realized, oh, it's been already corrected and it's just outdated. So anyway, NLTK is really common and like used all the time. Regular expressions, regex is usually called. It's really a useful thing. It's a little XKCD comic, but basically it allows you to structure your search essentially for certain patterns. So for example, like in this little comic, I think they're looking for an address. They say like, oh, like you think of an address is formatted the same way almost every single time. And you can basically structure like, well, I know there's going to be an address number, a street name, you know, it's going to be drive, avenue, lane, whatever. We have like a city, state, if you're in the US, a zip code. Like you can see the structure of an address every single time. So regex basically allows you to find those patterns and look for those things. So it can be really useful for feature extraction itself and processing text. Again, there's a whole lot of stuff. Regexr, xr.com. I really like this tool. Basically, you can post whatever text in here. You can try it out. They also have some cheat sheets, which is really nice. You can actually tell you what all these things different mean. I'm not going to go through them right now because I think they wouldn't really help too much. But no, basically, like you can say a range of letters, a range of different characters, actually what you're capturing. So like this thing, I want to capture the street name in an address, and I also want to capture the state of an address. You can actually say these are the things that will be returned to you, but still follow this overall structure. And you can do some really fun stuff and really great stuff. That's why you can sometimes see these really crazy long regex expressions and everything like that, is because they're trying to find this pattern essentially. Okay, cool. There's also a little fun one is regex crosswords, which I came across last year, which I think is just really fun. You actually can do a little crossword puzzle with basically regex, and so you can actually say, what should this letter be, for example, or like what would cause actually say if this is true or not. And you can see, oh, there you go. And A would basically A or Z, A or B. So anyway, it's kind of fun stuff, but it's in the notebook. Okay. Cool. I'm kind of going pretty quickly, but I think pretty good so far. Any questions? Good. Awesome. So let's talk about actually processing this test. So I have some code, yay, code, right? So let's check out NLTK. I hope I have in the right environment. Okay, we'll see. And so I actually have this data source right here, which is A Christmas Carol, which is literally the book of A Christmas Carol, because it is open domain, so I can actually run this from the Gutenberg project. And so you can see this is what the text actually looks like. You can see all that good stuff. Oh, look, the end, plus some extra information. So I'm actually going to go and take that file. I'm going to read this. So this is probably a while since you guys seen with open, because we've been spoiled with pandas, which can read files really quickly and easily for us. But note that this with open basically is allowing us to open up the file and making sure we should always, like, just like when you open up a book and you start reading it, you should close your book afterwards. That's kind of what's going on here. There's a reason for that. A part of it is, what's it called? The actual memory usage of when you open and like reading a file and stuff like that. Basically, if you leave your file open, your computer might not reallocate those resources, and you can crash it in really big text. So that's how we're using this with open. But basically, it opens up that file, treats this as this is now my file. So now we can actually work on this. And this right here, hey, look, list comprehension. And what's nice is that this guy right here is a generator. I don't know if you ever talked about generators, but basically this is kind of nice. It's kind of like range, right? Where basically say, hey, give me the next one. Give me the next line. Give me the next line. Give me the next line. And it'll go through that. In this case, I only do it for 20 lines. So you see 20. Or I skip, actually, I'm sorry. I skip the first 20 lines and go on for 500 lines. Okay, and so you can see this. There we go. And you see this right here is that it's a list comprehension. So basically it pulls up each line. See, it's a little messy right here. There's the next line right here, and you can see a little bit of what's going on. If I then instead change this to like 50, you can see here is that I'll actually have further down the line and everything like that. Okay. So, yeah. All right, so that's what, anyway, I'm opening up the line, printing out the lines. I can actually say, okay, well, what if I wanted just one big text together? I can join it. So there we go. You see the original stuff right here. And then we can actually do the opposite of this, which is kind of like what this is. But now it's going to have this huge, like it's read each line, it's combined each thing together, and now we're going to split it by spaces. So that's what this dot split does, right? If you guys recall. And it'll actually split up each word now. So every word now is on its own separate element in the list. Okay, make sense? All right, cool. So now we have our stuff like, okay, we need to do some cleaning. Well, what does that mean? Well, cleaning is basically going to be getting rid of some extra stuff, things. And I'm not going to go into full detail, like using my full regex. Cleaning can be a long process. But for example, like, I don't want this. This is ugly. Like, what's the point of this? Cleaning might also include just like getting rid of things like capitalization and stuff like this. But we'll talk a little bit more about that. Okay. All right. Oh, Beautiful Soup is a useful tool when you already have an HTML. It's not the only tool. Some people like different ones, but I personally like Beautiful Soup because that's what I learned early on. You can get rid of some extra like HTML tags and stuff like that. Okay, so we're going to do normalization. That's kind of a part of our cleaning process. So normalization basically gets rid of the capitalization, punctuation, like we mentioned before. So capitalization is really easy, right? Just dot lower. Boom. Look at that. Everything's lowercase. All right. We're getting more. You know, this text now is getting like simpler and easier to deal with. And then let's get rid of punctuation. It's like, okay, well, we want to get rid of anything with punctuation. So we actually are going to use some regex here. So this is import RE. So that's just regex, right? Regular expressions. And then we're just going to get this new clean right here. And note that I am passing, I believe, yes, I'm passing this guy right here. So everything's already lowercase. So I actually don't need this uppercase here, but that's okay. And what this is basically saying, hey, this is a regex string. So that's what that R in front of the string is doing here. And basically, this is the pattern I'm looking for. And basically saying, hey, basically anything that's this thing, like that's, I'm sorry, anything that is not, that's the not for regex, that's not an A through lowercase z, capital A to Z, and basically 0 to 0, which basically just all numbers, just remove those, like substitute it with a space. So that means I should get rid of, you know, this symbol. I should be getting rid of periods and stuff like this. So I run this, hopefully, there you go. You can see, hopefully no punctuations. Note that there's still a lot of extra space here. I also got rid of, I believe, yes, I like note that even though it says \n, yeah, \n, this is actually getting rid of that as well because that is a special character by itself. So it's treating that as one character. And that's why you don't see any \n's. Okay. But note that also I got rid of like Marley's ghost, apostrophe S. I got rid of the apostrophe S. But that's okay because does it really matter if it said Marley versus Marley's? We're probably not really need that information. Okay. Any questions, comments? Yeah.
I just want to mention that that R for the regex is stands for raw, and it's it's for raw. And what it basically is saying that there's no special formatting in there, so that you can avoid a lot of the issues with escape characters and stuff. So yeah.
Good point. Yeah. So this is why, like, sometimes you don't necessarily have to have this, but it's like you said, Alvaro, it does help you a whole lot. And so I kind of think, I don't even know why I do this, but like in my head, I only use raw like R in this way for regex. So in my head, I think I even said it's for regex. I even call it like regex and everything like that. So good to point out. Okay.
Cool. Why didn't they get rid of the zeros up in the first couple lines?
Why didn't it get rid of these guys?
Yeah.
Let's hear what we have originally. Huh, yeah, that's interesting. It might be because, honestly, it might just be because my regex is wrong. I almost wonder now. Let's try that. Because I can just rerun this guy. Yeah, I'd have to look into that.
Maybe they're actually O's by accident.
Maybe. Huh. Yeah, I'm not sure. Okay, I'm not gonna, I was about to go like copy and paste that, and like you can actually see the order, like the character, see if it's specifically 0, but I think it's a 0. So I'm just surprised because does it do that for August too? Yeah, it does it for August too. I have to think about that. Maybe it's because I have 0 to here.
Yeah,
I mean, like you got me.
It is a 0 because it says up top, it says March 4th, 2018. And then down there it just says March space, whatever, the 0.
Yeah.
So it's weird. It took out the 2, the 1, and the 8.
I think the safer thing, okay, let's just see. We're gonna take half a second to see if we can do this. No, that didn't work. See, this is where be better than me, guys. Do better regex. But yeah, that's weird. I guess you could probably remove that afterwards.
I think if you put the /D and then the asterisk, you can probably take the numbers out. Because I remember using Perl, use the asterisk.
Yeah, I see. This is where like the regex comes through. Like, all right, like let's start doing things, right? So /D should be digit, and let's say star. I think there's one or more of them, but I think that's not what we're gonna do here. I think it's gonna give, yeah, that's not what we want, because now it's looking for that specific pattern of this guy right here, and it's not gonna take that. That's why we have to do, in this case, when I did 0 to 0, it should get rid of a range of numbers. And that's why I'm curious why it didn't do 0 though. So anyway, I'm sure someone's gonna look at this right now and try to figure it out. So if you do and you guys figure out what this is, because not pay attention to me, that's fine, I guess. But there's definitely something better you can do. And this is why, again, I say every year, I'm like, yes, I'm gonna do better at regex. And of course, this happens. But good catch, Mike. Yeah, this is where like you should always check out your, like, this is why it's a good point actually to print out your stuff to make sure this looks like what you'd expect it. Like that's why you shouldn't just assume, and make sure your test cases go through. There's more formal ways you can do it, but it's always good to print it out. Okay, let's go on to tokenization if you guys are cool, ignoring that 0. All right, so tokenization. So I mentioned about tokens, and basically you can think, the reason I call it a token is you can think of them as words, but that's not the best way to necessarily think about it. It's better to think of it as it's a symbol that represents some point of information. So the reason why I say this is because you might have a tokenizer where you have NT. NT is not an English word, but it could be a token. And basically that token could represent, not, or like if you had isn't, and you have this, the NT, that NT could just be the actual isn't part, which really means not. So note that tokenizer, like when you do tokenization, you can actually have different tokenizers. And what's really cool, NLTK actually has a lot of tokenizers that you might find useful. For example, you can actually, for sentence tokenize, you can do that for sentences. You can actually tokenize by sentence. You can token by word. So it's kind of like split. It's a little bit smarter than doing that. So it considers things that maybe not be words. For example, if I had like NT, like I mentioned, it might actually consider that as a real token. There's also regex tokenizers, which means that you can actually define your own, what you define as a token. And that can be useful for different, if you're pulling text, if you're familiar with your corpus of how it's actually structured, you might actually want to include certain things or exclude certain things that are not, considered words in your natural language. And then there's also like this tweet tokenizer, which I think is really important to kind of point out, which is awesome that's built into NLTK. But you think about this, it's a hashtag, hashtag blessed or something like that, right? Means something different than just blessed, right? Like hashtag is an important aspect of tweets. And so same thing with @ symbols. So that should be really treated as its own token by itself. And so it's important to recognize that. And that's where you should always be familiar with your corpus and what the conventions are. So anyway, it just basically breaks apart into something that is a single unit that you consider like a meaning. And that's why sentence tokenize, we could break it by sentence, but in this case, we want to break it up by words. So we're going to do the word tokenize here. We're going to use that clean, and we'll probably see the 0 in there. Well, this is now just a list of the words. So you can say the Project Gutenberg ebook, so it's kind of like the dot split, and I bet there's that 0 in there too. There it is. I don't know why that 0 is in there, but anyway, it should split them all across there. Okay, sound pretty good? Cool. So now we're just going to keep removing down information. We're going to get rid of stop words. So stop words are kind of like basically not really important words. Think a, the, you know, those kind of things. They don't really give extra meaning. So we might as well just remove it. Basically, it makes our data set smaller. We have less information to consider, and they don't really like give that much information. Usually we have like a list of common words. You don't have to think of them yourself. So that's really useful. And especially if you're using for different languages and stuff like this, they'll have different stop words. And note that it's dependent on context of the task. Again, like I like to say, like tweets, for example, like the way people write online or in a text message is very different than people writing, you know, like books and stuff like this. So you have to consider what your source is. Okay, so you can see here, all I have to do is just import stop words from nlk.corpus, and just know I'm saying specifically the words from English. And then I'm also getting rid of Christmas, because in this case, I'm like, you know what, Christmas is not really that important in Christmas Carol, because like I'm like, I know they're gonna say Christmas like 1,000 times, and it's like, it's not really that important, so I'm just gonna get rid of it. So that's the kind of thing I'm talking about in context. So now you see there, and if I do this, there's my word. So these right here are all my stop words. So you see I, me, my, myself, we, all that fun stuff. So you can see like this, at least based on what this stop words list is, these are considered words that don't really give that much more information. Okay. So, and again, you can argue saying, well, maybe this word is actually really important for the context of this corpus or text. I guess it could be corpus too, but you have to decide that based on your knowledge of the actual text itself. All right. So then if I want to get rid of the stop words, question, yeah.
So if we wanted to exclude a stop word, would we just put like minus where it says, yeah, there?
Oh, so you like want to get rid of it? Yeah, you can't just do minus, right? Because like,
Yeah,
if
like how does it, like if we wanted to include down and we didn't want down to be a stop word, like how would we exclude that?
Yeah, so that's actually, you can do like, I have to think about if this removes, well, let's try it out first.
And you could do that, or you can do a list comprehension and exclude that one word.
Yeah, that I think this might be more efficient. List comprehension could work, but like if you did list comprehension, if equals down, but that's usually not super efficient. Usually this is a little bit better. I forgot dot remove return doesn't return anything. It just removes it from the list. So this should now remove the word down, which, well, I don't know. There was up, so I think down was over here.
Yeah.
So yeah.
Cool. Thanks.
Yeah, no problem. Yeah, and note that, like I said, like all these words, a lot of them are prepositions and articles, like things that you don't really need. Okay, so if I run this now, run that just to make sure it's consistent. We're just doing a list comprehension, W for word and word carol. So this take all the words in that a Christmas Carol that we cleaned already, and basically say if W is not in these stop words, then just go ahead and include it. So this is relatively inefficient because we have to go through the whole list anyway. So if we run this guy, it shouldn't take too long. Boom, there we go. So we get all our words, but no like, oh, see, dang, stinking 0. Oh, that's gonna kill me now. All right, I have to figure that out later. But anyway, yeah, Jessica.
And could you just, or I don't know if it wouldn't be the most efficient, but could you just add that to your list of stop words, like the 0, the 00, the UNF, like all of those?
You can, but you shouldn't do that.
Okay.
You should definitely, the reason why I'm saying is in this process, you should definitely think of like when you're getting rid of cleaning this text, that's where your cleaning should be done. So you could technically do that, but if you were to see this in the real project, like you're like, oh, I missed a 0. Don't just add it to your stop words. Definitely add it to your cleaning process. Because then what happens if you change your cleaning process or you change your stop words, but you forget that like you added this weird 0 in there that's not technically a stop word just because you messed up your cleaning, then you can have some issues later on when you modify things. But yeah, you technically could. Like I won't because it just is a reminder of my inadequacy of regex. So.
Oh my gosh, thanks for the answer.
All right, no problem. Okay, so all right, we got our stop words removed. Let's start with, okay, so this is where we start getting some more advanced stuff, stemming and lemmatization. So I think for the most part, this seems pretty like, all right, seems pretty good. Stemming, I think, and lemmatization starts feeling a little weird because like, I wouldn't have done this myself, but there's a reason. So stemming basically is going to reduce the complexity, but still have meaning. So the idea is that we have in English especially, we have many different forms of this, basically the same word. Think of drive, drove, like so that basically means the same thing, but we just have conjugated verbs, right? You might have other things like that. For example, like let's say isn't, well, that's the best example, but you would have words where it's like, oh, really drive and drove are the same thing. So we should just drive. Or think of like unicorns and unicorn, like that's the same thing. Like we don't really want to consider those as two separate things. We might actually go ahead and make that into what's it called, into one token, essentially one central meaning. Now I said stemming, and I should have said like drove and drive. Drove and drive will not be processed on stemming. So stemming is really fast. It's also crude in the sense that like basically it's just going to do the easy thing. It's like, hey, there's an S at the end, boom, no S there. But it's not going to do it like look and say, oh, where's the unicorn? Oh, unicorns, take off the S. It's going to make does, like, oh, the word does for whatever reason it's in there. Oh, let me go get rid of like the S on does, and you have DOE, and like that's now the word it represents. It does a few things like that. And just know that not all stemmed words then are actual words, they're just tokens. So a good way to just show you guys this is just applying this stemization. In this case, I'm using Porter stem from NLTK. But if I run this now, you can see for the most part, yeah, all the words look pretty much the same, except you can see something like, what the heck is this guy going on here? So you can see what this original one is. Oh, this is not going to do that. Where is this going? Oh, well, this is a better example. House. This used to be house. It's not house anymore. It's house, I guess, without an E. I don't know how you pronounce it without an E. But basically, this stemming tool basically is just getting rid of common like endings that don't really matter too much. And so it makes it easier for us to process and say, these are all the same words. And so it's going to get a lot of like rid of like the S's at the end. It's going to get rid of E's at the end because it's like, oh, like might as well get rid of it. ED, because so many common words are just conjugated with ED. It just gets rid of everything with ED on there. So it makes it nice and simple for you to combine words. But just know that not every word in there or every token is going to be a meaningful word by itself. But it's really fast because it doesn't have to think too hard. Okay, does that make sense what we're doing here? Cool. The similar process is lemmatization. And lemmatization basically says, hey, I don't want to just, I'm not crude like stem. I'm going to take my time and think about what's this actual word. So this is where drive and drove would actually be the same word and would convert over drive and drove together. I think this might be harder to see, but you can get the idea when I process this through. You can see it took a little bit longer. So look, that took a minute and or a second and a half. This one took 16 milliseconds. So you can see like the difference in speed and stuff like that. And that's a relatively small text, but you can see that basically everything in here is the same word, and we didn't get rid of S or like ED at the end or anything like that. So it will try to make it into a single word using a dictionary, which does take time then, which is why it takes a little bit longer for it to look up and see if it knows what that word is. Okay, that's lemmatization. All right, sound pretty good? Awesome. All right, we have a few more minutes left, but let's go, keep going. So I'm just going to mention really quickly, I don't know if this is actually talked about in the curriculum. There is parts of speech tagging. I'm going to kind of skip over it a little bit because it's not super important because, well, I shouldn't say it's not important. It's that it's not as common because you have to have a corpus that already has parts of speech tagging. And I will tell you right now, the people who have to do parts of speech tagging, I don't know. It's like the worst homework assignment possible because like essentially they have to figure out each word is like a noun, a verb, an adjective, you know, is it the verb predicate? Is the noun predicate? You know, like, I don't know, that sounds awful. But so someone has to do it by hand essentially. And so you can, if the corpus does include parts of speech, it can be super useful. But in general, you'll probably not come across too many data points that, or data that actually have parts of speech tagged, but NLTK can process it. And you can see this fun little little diagram. Has anyone like back in like English class, like done any of this, like when you actually map out the sentences? Thumbs up if you have. And I see something like, I have no clue what's going on here. Yeah, that's usually the reaction. It's like, oh yes, I remember this. And the other one is, I have no clue what you're talking about. I think this has died out of practice. I don't think many people actually do this anymore because it's a lot of work. But it kind of gives you an idea of like how to interpret the sentence. So when you have parts of speech, you can actually understand what the sentence means. So for example, like I shot an elephant in my pajamas. So in my pajamas belong to I. So I shot an elephant and I was in my pajamas. But if you were and said, I shot an elephant in my pajamas, meaning the elephant was wearing my pajamas. And so I shot the elephant that was wearing my pajamas. So you can see that even though it's the same sentence, it does structure it differently depending on what you define as parts of the speech. And usually in speech, like when we talk, at least in English, we use emphasis of being like, I shot an elephant in my pajamas. Or you say, I shot an elephant in my pajamas. Like it's kind of like you use the emphasis in there to kind of size, but even that's super confusing. So this takes away some ambiguity, but you can see how difficult this can be if you do this for every sentence by hand. So I'm not going to talk too much about it, but just know NLTK can process it. Okay, cool. So let's see here. I actually, how much more do we have left to go over NLPK? Oh man. Do I just talk too much, guys? Is this why like we can never get through everything? Let's see here. I'm trying to think. So we talked about intro NLPK, NLP, text processing. We didn't get to feature extraction and embeddings. Would you guys like to just kind of go a little bit longer for feature extraction? And then I think what we'll do for like our office hours stuff, we can talk a little bit about embeddings and stuff. But I think feature extraction, well, let me just see what's in here real quick. Yeah, we can go a little bit, maybe like 10 to 15 more minutes on feature extraction. What do you guys think? Sound pretty good? All right, cool. Yeah, hours never enough, right? Maybe it's just because I talk too much. I don't know. All right, so let's talk about feature extraction. So at this point, we should have processed our text. We're now ready to do interesting things, right? I don't know, cleaning's kind of interesting, but we say, okay, let's get some meaning out of this actual feature, out of these natural language. So just know that basically your features do depend on the task, right? So that means like, do you talk about the document level or do you talk about the word level? Like you need to think about like, what is the point of what I'm doing? If you're doing machine translation, translating to another language, you likely are thinking about word level. But if you're looking for sentiment, you probably just look at the document level. You don't have to look at the specific like word per word within the sentence, okay? So just kind of always be aware of what you're doing versus like just throwing things at it. It's like, oh, I don't know, just do this. So that's always the first step. So one of them is bag of words, which I kind of mentioned very briefly. Basically, it's just an unordered set, a bag of tokens representing a document. Basically, you say, hey, is there a word in there? You're like, or is this word in the document? And that's essentially what you're doing. So obviously, you're losing some information, but in a lot of ways, we might not really care about that specific ordering information. It might be good enough just to look at saying what words are actually being used. So what I have a knowledge check here. We can simply keep the tokens as separate sets, but why might this be a bad idea? So if we actually have these as separate like sets in there are some issues with this, is that basically if you were to do this for each document, you'd have different sizes, different words, right? Think of like if you had one document and you made it backwards and made another document backwards, like the problem is you would have two separate now like different size things, and that's harder for us to do with machine learning and stuff like this. It's also harder to compare now, like it's like, oh, like, well, this had one set of bag and this had another set of bag. How do we compare these two documents together? Are they related to each other? Are they close together? And then also like if we have multiple times, if words are appearing multiple times, it's not distinguished as like saying, oh, like we had this occur so many different times. So bag of words is kind of like a very crude, like very quick way you can do something, but it might not be the best way because essentially you just say what words are being used, which is not, if you think about language, right, that's not always the best thing. So the better idea is vectorization. So in this idea is that basically we take a document and we're representing it as a vector. So when you say, whenever you think vector, think like a row of numbers or a list of numbers, right? And we can do this in a bunch of ways. So one way we can do this is document term matrix. Basically, the rows themselves are the actual documents, and the columns would be its tokens. And the values in there are basically saying how often those words occur. So what that looks like, this is where, let's see if I actually wrote it. Nope, I didn't write it. Oh, maybe. Nope, okay. I'll just show you guys real quickly what this would look like. And I think this is where the curriculum, who's ever read the thing that they talk about like vectorization, like in the way of like bag of words and vectorization? Okay, good. So essentially what you look at is a matrix, and like each row right here is like essentially a document. I'm just gonna say a sentence. So like I can say like, Sally went to the store, right? So I have something like Sally in, I don't know, store. And then I have another sentence that's like, Sally bought a puppy. Why not? I'll just put bot for, I'll just put B for bot and then like puppy, P for puppy. Okay, and then you say, okay, Sally went to the store. Sally went to the store. Sally bought a puppy. that's another sentence. And say, Sally went to the puppy store. Went to the puppy store. I'm trying to think of something good. Sally brought her puppy to the puppy store. Let's just go with that. So Sally brought her puppy to the puppy store. So I'm just making little tallies. So you can see basically the frequency in there. And if we never use this word here in this document, it's just considered a 0, right? So this way you can basically have your vector would be like 1, 1, 0, 2, or 1, 0, 1, 1, or 1, 1, 0, 0. So the idea there is that you now have a vector representing of what words are there and what's represented. And this way you can actually have, you know, multiple, like basically every time there's a unique word, you just add it onto your list and stuff like this. So the row, in this case, the column size would be, if you included everything, the number of unique words. Make sense? Cool. All right. So that's one way we can do things like that. I mentioned like there's a little knowledge check here. How is this better? We kind of, I think you guys can figure out like it's better in this way is that like we now include multiple words. We now can look at how things are in common. Can compare the similarity. So like, for example, Sally went to the puppy store to buy a puppy. Like it's going to be similar to Sally bought a puppy. Now you have like similar words, even if it's not the quite same frequency. So it makes it a little bit easier. And what's really nice is that we can actually use cosine similarity because they're basically vectors. We can say how close are these vectors are together. And basically, I mentioned like, why don't we do a dot product? There's a few reasons why in this, but like the main thing is that to consider is that we use cosine similarity because we're seeing the angle, the difference between this vector space. A dot product, you could technically do this, but you'd have this weird, like, one of the issues is that you would have, if something's orthogonal, not orthogonal, anti-parallel with it, it might be harder for you to actually determine like, what does that mean? So cosine similarity tends to be a little bit better for this. So I'm kind of skipping over this. So time. Make sense so far? Cool. All right. So here's some other things we do. TF-IDF, or I think I've heard someone say TF-TIF-TIF. I don't say that. I say TF-IDF. So one disadvantage to bag of words is each word is equally important. So if you think about that, like there's not a distinction of saying like, oh, like even though we have the frequency of the words, we don't really say like what word has the most meaning to it. And so we can actually do something really cool. And one of them is basically is TF-IDF. Basically it's saying, hey, if this word only occurs once in all the documents, that's a very defining feature for that single document. Like if the puppy only occurs one time, that's an important document. Like that puppy word is actually a very important aspect of that document. It defines that document a lot, right? So the idea with TF-IDF stands for term frequency and then inverse document frequency. You can actually calculate this directly, but I just kind of wrote this general thing. Basically the idea here is like, hey, how often does this term actually occur? And then how often does this actually occur with a document? So how many documents does this actually occur to? So TF, count the number of count of term in a document divided by count of all terms in a document. So basically saying how frequently that word is used, like say puppy, 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 like through the whole thing, you would have a higher number here. And then IDF, now this is where I think people kind of like, why are we doing log? It just ends up being a lot easier for us to do the calculation on here. There's not a, like, at least from my understanding from it. But the main idea here is that we say, okay, the total number of documents divided by the number of documents with that term. So the idea there is basically saying how frequently does this word, this token occur in other documents, okay? And the reason why we do this is basically just to make the calculation a little bit easier for us to deal with, okay? So that's really what TF-IDF is. Not complicated at all, right? But you can kind of see a little bit, we can see how important, and importance basically means the rarity, like how rare something is being used. That's probably an important word for that document, okay? Sound pretty good? Cool. Oh, that's only 5 minutes I went through this. That's pretty good. All right, so the last thing is word embeddings. And this is where, let's see how big, this one I might actually go back to maybe in the future, just because there's a lot we can talk about word embeddings and all that good stuff. But another feature we can do is word embeddings, which I think is one of the most fascinating things and kind of encompasses a lot of like issues that we have with other things. So one is that we actually have a more condensed way of representing a document, or I should say like, you know, a text. And what's cool about that is that we don't have to then have this very, very long, like imagine you have 20,000 different unique words in like a corpus. Corpus meaning multiple documents, right? And you would have a huge vector. And having a huge vector makes it really difficult to find patterns in it. So word embeddings, essentially, you can think of it that you're trying to compress the information into something that's reasonable to calculate with. And so there's some strategies you can do with this. The curriculum talks about a bunch or a few, and I'll kind of go through a couple of them, but I'll come back to this maybe in office hours one day, because one of the things you can do is actually use a neural network to actually build up your word embeddings, which is, I think, is the coolest thing in the world, because it's really, I think, really clever. But anyway, the main idea, let me get rid of this little block in my way table of contents. There we go. Okay, so this one actually, I think I took this from, oh, I don't reference it. There it is here. That's good. I'm sorry. So it actually comes from their machine learning course from Google. They actually have talked about a whole bunch about word embedding stuff, but this is the classic picture. And so the idea here is that an embedding, a vector, really is like a list of numbers, and you can think of it when you have 3 numbers in your vector, you like think of like a 3-dimensional space. If you have 10 numbers in your vector, you're thinking of like a 10-dimensional space. So we can think of it like a hyperdimensional space. But the idea that there's some point in space, when we say a vector, you can think of it as a point in space, in this multiple dimensional space, and that's representing a single, like for example, a word. And what's kind of cool is like, well, what words are around it? You know, like what other points in the vector space are there? And what's kind of cool with word embeddings is that, or embeddings in general, is that you can kind of think about it in those terms of being like, well, what is around this? Like what is near? And in general, what we try to do is kind of like clustering. You kind of assume things that are close together have some like relationship with each other. Like they're closer together. Like if you have something that's closer in higher dimensional space and something that's farther than in higher dimensional space, you expect that this is approximately the same thing. So that's kind of the idea here. And so what's cool about that, because we have different dimensions, the embeddings kind of like shortcut us having to remember every specific word. And so you can kind of think like, I think I gave this example in a one-on-one with another person at one point, but you can imagine like, let's say we have like a vector that's only a size 2. And all that's in here basically is something like this number right here is going to represent gender. And in this case, I'm just going to use man and woman just because they're just defining it this way. So let's say man and woman is like the 2 genders it can be, and then royalty. And this royalty is just like yes or no. Okay, so royalty. So let's just pretend like royalty, right? If you are royal, like that is a 1. If you're not royalty, you're a 0. And let's say we have gender is, let's say 0 is woman and 1 is man or something like that, okay? This is just really simple stuff, but it's not really gonna work like this, but it's gonna help us. So if you think about it, if I said something, and you can probably see from this picture right here, if I said one being is male, okay? So I put 1 and 1, what word do you think that represents? So it means you are male and you are royalty.
King.
A king, right? So you can now represent like this idea of a king right here. Like, oh, look at that. And then you say, okay, what if we hadn't said 0 here? It would probably mean it's not royal, which in this case we say man, or you know, could be something like guy, right? So guy would likely be near right by this part. Maybe for example, guy might be like 0.1, and like man is like 0 for royalty for whatever reason. But the idea that it's like it's close together, this thing's here. But what's kind of cool is that we can actually define like, you know, woman and queen, and you can see this like direction here. It's like what's cool about embedding is you can say, well, if you move in this direction of royalty, let's pretend it's the 2nd dimension here, that royalty now is like, well, we can shift everything that was man and let's say, or say, I should say gender. Let's say man and king over here, and we shift it in the direction of gender closer to, let's say like female gender. I'm kind of mixing up sex and gender, but that's okay. So we're just going to move across in this direction. Now we have woman and queen and things that are like this. If I added a 3rd one here, let's say age, right? And saying like 1 is 100 years old, 0 is like not very old, right? Say like you're just born. If I had 0 in here, I had 1, 0, 0. How would you interpret that? Or what word could that possibly be? 1 being male, I think 0 being no royalty, and then 0 being young.
Just a child.
Yeah, it could be like a baby boy, like if that was a word, but like a child, right? So this would be kind of tough to say. If there's not, in English, there's not really a male word, but you might have things, for example, like certain associations that might be associated with a male, young, non-royalty. If I instead had something that's a royalty here, the one I have, let's say is, I think it's a male. So male, royalty, and then 0 for like young. That would be like a prince, right? But if I change this to a 0 here, that would be princess, right? So that's the kind of idea of what embeddings do. They kind of are a shortcut. And what's cool about it is that I can kind of build this as like, oh, this is gender, this is royalty, this is age, and kind of make my own embeddings. What's really cool is that you can say, hey, like machine learning algorithm, you figure out what's the best way to condense this information to represent it. And what's cool is that once you have that, you can actually travel with the vectors and do mathematics on the vectors and actually represent and figure out different representations of what this embedding actually means. So it's kind of cool. You do get some weird stuff sometimes. So for example, let's say we had like on the same, okay, this is actually a great example, country and capital. This is going to be trained based on what is given the data, so its corpus of information. And you might have an embedding where it's like, oh, like turns out like, words that are very close to this direction, like all these countries, and you shift them in a certain direction, and it looks like they're capitals. But that in practice actually isn't what's going to happen. What's actually going to happen, because you're training it on like what's the things going on. For example, if I have like, let's say the United States, and I take like California, or let's say the US is in here. And originally you look at this like, oh, it looks like the capitals, like that's pretty cool. And you say, oh, let's do this transformation, that same direction transformation with the US. You might not be getting Washington, D.C. You might get something like New York or Los Angeles, where maybe these are just the most well-known city in that country, because basically it's just based on the corpus itself. So there's not direct, like you can't expect it to understand from the training exactly what it's doing, but it starts building up structures to do shortcuts. And there's a bunch of ways we can do this. This is where, for example, Word2Vec, Glove, you can do these things. Another thing is something called autoencoders. And essentially, I'll just kind of mention the autoencoder, but it's kind of cool. Essentially what you do, you start off with your words to begin with as inputs. Think of like the document term matrix and being like, oh, like, it's like the word is, queen, and then like 000, right? And basically you have these neural networks that basically get smaller and smaller. So you might start off with like, let's say 20,000 different words, and then you get smaller, like let's say like this direction. And then the output is also gonna be 20,000. It's just the word itself. And what you do, you train the neural network to say, hey, adjust these weights and biases coming from the hidden layer, adjust those until you basically have a pretty close up, like pretty good at basically guessing, or not guessing, but predicting what the word should be. So if I input the word queen, it should come out the word queen at the end. And we can train it to make sure those biases those weights and biases are the proper numbers. And once you get a good enough accuracy, what's kind of cool is that because it had to figure out just from this hidden layer, it doesn't know what this input layer is anymore to get this output. This hidden layer right here actually, in a lot of ways, has information about how to get from here back to itself. Does that make sense? Like, it's kind of like building up this little shortcut. And what's kind of cool then is like, well, we can actually make this relatively small. Let's say you have like 20,000 words and you make this thing like 100 or 200, neurons, stuff like that. That's a much smaller feature space versus 20,000 different data points. And now you can actually use these embeddings now, which are just vectors. You can actually use those to now, actually like do your analysis and predictions and stuff like this. And that's what a word embedding can represent. But in general, when we say embeddings, what we're talking about is something that is taking information that's much larger and kind of condensing it down, embedding it into a smaller vector space. So that's kind of what's this embedding is. So maybe we'll talk about the actual details of how this works and how we can build this up in a future office hours and stuff like this. But I won't keep you guys any longer because it's a little bit longer than an hour, and I think that's it's a lot to ask for someone. But did you guys have any last questions or comments before we close off here?